Homotopical group theory is usually solved as studying properties and group theory through classifying spaces. Now, classifying spaces is something that we study in homotopy theory. So we want to see what the relationship between properties in the homotopy world and properties in the group world. Now, when I talk about group theory, what kind of groups do I mean? Well, I mean mostly finite groups and compact Lie groups. So in this series of talks, I'm going to sort of separate in two halves. The first two, I'll be talking mostly about finite groups, and the second two about compact Lie groups. There is a slight difference. I mean, finite groups, as we know, they are more combinatorial. I mean, they are finite. So actually, the homotopical group theory of finite groups is more combinatorial than this one, where you have more elements of homotopy theory. That is more topology. But at the end, well, depending on time, we'll see. We'll see that we actually can combine both theories in one that is combinatorial, even for compact Lie groups as well. Now, regardless of how homotopical group theory is solved, most of the times what we are interested in is in trying to understand the homotopy type of the classifying space of a group, but completed at a prime P. Okay? Now, we haven't had any talk about P completion yet, but we will have one next week. But for now, just think about the P completion as the P primary part of a space. Imagine that your space was an abelian group. We know that an abelian group can be broken into pieces, one for each prime. So in a way, some spaces can be broken in a similar fashion. But I'm going to talk a bit more about it. Now, as a motivation for these first two talks, I'm going to talk about I'm going to give you the statement of a conjecture, which is not a conjecture anymore, the Martino-Pridy conjecture. So the Martino-Pridy conjecture is about understanding when two classifying spaces completed and a prime have the same homotopy type. So let G and G prime be finite groups with P CILO subgroups S and S prime, respectively, then the classifying space of G completed at the prime P is homotopy equivalent to BG prime completed at the prime P if and only if there is an isomorphism of the CILO subgroups, which induces an isomorphism of categories FSG to Fs prime G prime. Because there are many elements here that we don't really haven't really defined, like these things, right? These categories. But these categories are something that has combinatorial information about the groups, combinatorial information about the lattice of subgroups, P subgroups of the group G. So we are going from a statement about homotopy of classifying spaces to something that is combinatorial algebraic. Okay? So this conjecture is really what drove the P-local, the development of homotopical group theory for finite groups. And it's going to be a motivation for what I'm going to talk about. Now, this is not a conjecture anymore. Like I said, it's now a theorem. by Bob Oliver. And he proved that recently, 2004 and 2006, P odd and P equal to 2. Okay, now since my talks are gonna deal a lot with categories, I'm gonna start reminding you about some of the things that I'm going to use about categories. Okay, so I trust that everybody knows what a category is and everybody knows what a functor is. Now, what I want to understand is how to go from categories to topological spaces, okay? Now, fortunately, Fermin already talked yesterday about the realization of semi-simplicial sets, which is simplicial sets now, really. So what I'm going to do is, from a category, I'm going to associate a simplicial set, and then from there, I'm going to associate a topological space. So definition, let C be a category the nerve of C is a simplicial set given by, well, a simplicial set is just a sequence of sets, right? With some phases and some degeneracies. So I start with C0 is a set of objects. C1 is a set of morphisms. C2 is a set of composable morphisms. So the set of morphisms GH such that GA exists. Okay, and so on. So Cn is going to be the set of n tuples of composable morphisms. Okay, and this has the structure of a simplicial set given by, well, we can go up composing two morphisms. And then we have one less. And we can go down by taking one of the morphisms to be the identity. Okay? So this is a simplicial set. So now, using the geometric realization, Fermin, I can talk about the geometric realization of C. So the geometric realization of a category C is the space usually denoted by C between bars, or sometimes you will also see BC. So this is the geometric realization of the, or did I give it a name to that? Well, of the simplicial set associated to C. Is it clear what I mean? Yeah? Okay. Now, the geometric realization is functorial in a certain way. Well, we are going from categories to spaces. Now, between categories, we have functors. What happens if we have a functor between two categories? Well, that reduces a map of the geometric realization. A functor F from C to D gives a map of the geometric realizations. Okay? Okay. Now, to give a couple of examples that are going to come up, we'll just do a simple one first. So examples. example, if we have the category which only has one object and only has one morphism, really trivial category, right? What is the geometric realization of that going to be? Well, we only care in this talk up to homotopy type, okay? So the geometric realization of that is contractible, okay? Now, an example that Fermin mentioned yesterday, more or less, is what happens if we have the category where we have two objects. We have the identity morphisms, and we also have a morphism from this to that. Now, you look at it, kind of looks like an interval, right? And the geometric realization, it is homotopy equivalent to the unit interval. Okay? Okay. Now, in order to know the homotopy type of categories, we would like to understand better how the geometric realization behaves with respect to certain functors. Example, it will be logical that if a functor is considered to be an isomorphism, then what we get on the other side will be a homotopy equivalence, right? So, but now we have two different notions of isomorphism of categories, right? On the one hand, we have an isomorphism of categories is a pair, C and D, it's a pair of maps. Well, it's a map, it's a functor, F of C and D, such that it has an inverse, such that there is G from D to C, such that the compositions are the identity, such that F composed with G is equal to the identity on D, and G composed with F is the identity on C. I mean, I know I'm repeating many things that probably many of you know, but I want to start from the beginning. So be patient, there will be time to run. But there is another notion that is a bit weaker, which is called an equivalence of categories. So we say that F from C to D is an equivalence of categories if there is G from D to C. And now we don't want that the composition are exactly the identity, but that they are naturally isomorphic to the identity. There's G such that F composed with G is naturally isomorphic to the identity on D, and GF, the identity on C. Okay. Now, if we look at the first one, the isomorphism of categories, it should be clear that an isomorphism of categories is really going to give a homotopy equivalence, because it's actually taking each of the sets in the simplicial set, and it's giving you a bijection with the corresponding set for D, right? So in that case, there is no doubt that this gives us a homotopy equivalence. In this case, we had to think about it a bit more. So for that, we need to think of natural transformations in a slightly different way. So there is an exercise, which is not hard to do, which is that the set of natural transformations from F the natural transformations between two functors f and g from C to D. Now remember that a natural transformation is for each object of C, we give a morphism of D, right? And such that some commutativity occurs. Well, there is a bijection between these and functors from C cross that category over there into D. Okay, and that's not hard to prove. Okay, so now given that exercise, what happens? Well, if we have that Fg is naturally equivalent to 1D, this is giving us that we have a homotopy between the realization of F composed with G and the identity. So an equivalence induces a homotopy equivalence of classifying spaces. Okay? Okay, we will use that a few times. Now, sometimes it's not that easy to show that two categories have homotopy equivalent classifying spaces. And there is a very nice result by Cuidense that allows us to sometimes identify the fiber of the map between the classifying spaces. So to introduce that result, let me talk first about over categories. So given a functor from C to D and an object of D now we define the over category F going down over D. This, in a way, is the objects that are over D up to homotopy. So the objects are given as follows. Is first an object of C and a morphism from F of C to D. And this morphism is a morphism in D. And the morphisms, so say that we have two objects, one given by C1 and one given by C2. What are the morphisms? Well, they are maps, they are morphisms from C1 to C2, such that when we consider the diagram given by applying F and the maps that are given, this commutes. Okay? We have to think of that sort of as the fiber of the map in the wall of categories.
When you're saying classifying space, that's why you put the B on the C, or?
I should have said geometric realizations. I just, well, yes. I mean, sometimes you also call the geometric realization the classifying space. So, yeah. If I make a mistake, I'm using the two terms interchangeably. Okay, so now how is this category gives us the fiber when we go to the topological spaces? Well, notice first one thing, that if there is a morphism, if we have a morphism from D1 to D2, a morphism in the category D, then this gives us a functor from the other category. This gives us a functor from this category to this other one. Right? How? Well, if we have a map like that, then you compose it with the map from D1 to D2. That's it. Okay. So now let me state Cuidense Theorem B. So Cuidense Theorem B says that if we have a functor from C to D, and this is such that the map induced this functor induced is a homotopy equivalence on geometric realizations for every morphism D1 to D2, then the homotopy fiber of the realization of this map is given by the geometric realization of these things that we think is homotopy equivalent to the geometric realization of F over D for any object D. Okay, so these are very nice results. That's probably every result by Quillen is. Now these are, there is a theorem B, is also because there is a theorem A too. The theorem A is a particular case when all these over categories are contractible. And in that case, the conclusion is that these two categories are homotopy equivalent, the geometric realization. Yes?
Does he give a criterion to figure out which D?
Oh, well, you can pick the D that is easier for you.
Well, let's say you don't. If you drop that assumption on the equivalence on realizations for morphisms of D, if you don't have that, is there still like a criteria?
Then, well, then it's not that easy to figure out what the homotopy fiber is. Yeah. Yeah, I mean, you need that condition for to really identify it. Okay, so I think this is everything I wanted to say about categories. Right. So now let me go to what I really want to talk about. So one, classifying spaces. Now, we've already talked about classifying spaces in this workshop. I mean, we talked about KG1 a few times, and these are going to be really the same spaces. But when you talk about KG1, you give a condition that this is a space that is unique up to homotopy and is determined by certain conditions, that pi1 is equal to G, and all the other homotopy groups are 0. Okay? But I want to give a specific model for this space. Okay, so a specific space. So let G be a discrete group, and I'm going to construct a category associated to this group. So consider the category BG with this strange B. whose objects, well, there's only one object, and the morphisms, the set of morphisms, which is now only morphisms from the point to itself, is given by the group G. I also need to specify the composition. Well, the composition is given by multiplication in the group. Composition given by group multiplication. Okay? All right, so that's it. Now what I'm going to do is take the classifying space of this category. So definition. In this definition, I'm going to put it in quotation marks because now I'll explain why. We define BG, the geometric realization of this category, is the classifying space of G. Now, why did I put quotation marks? Because usually when one talks about classifying spaces, one talks of a space up to homotopy, right? Only of a homotopy type. So here what I'm doing is giving a specific model. So to be more precise, one should say BG is a model for the classifying space of G. But I don't want to be saying that all the time, so I will just say classifying space. Okay. Now, like I say, I want to see what parts of group theory go over to homotopy theory, right? So one thing in group theory is to study homomorphisms between groups. How does this behave with respect to that? Well, if I have a homomorphism, from G to H, well, that gives me a functor from BG to BH. So that gives me a functor from BG to BH. And when I take geometric realization, it gives me a map, a continuous map, from BG to BH. So what I have constructed here is a functor from groups to topological spaces. So B, we can look at it as a functor from groups to topological spaces. Okay, so let's look at some of the properties of these functors. Some properties. Let's look at some maps that really show up a lot. For example, if you have a subgroup of a G, or if you have a subgroup of G, what is the map corresponding to the inclusion? So 1, if H is a subgroup of G, then we have an inclusion, right? See that the inclusion, that gives us a map, BI, from BH to BG. Okay? Okay, so what I'm going to say is that this map is up to homotopy, up to changing the homotopy of this guy, changing by a different model. This is a covering space, but it's up to homotopy. A covering space with G over H sheets. Okay, now let's see that. It's not hard to see. This description. So let's look at BI and let's try to apply Cuidense theorem B. Okay, So what do we have to see? We have to look at this functor and consider the fibers. Okay? So now here there is only one object. So we only have to look really at one fiber. That's good. So let's consider the category, this category. Now the objects here are given by pairs, where the first pair is, well, the only object that we have an H. And here we have the image of the point, still the point, and a map from the only object to the only object. And the morphisms here are elements of G. So this is an element of G. So the objects are really elements of G, if you think about it. And the morphisms, well, if we have two objects, say G1 and G2, so a morphism has to be a map from the point to the point in the initial category, such that when we apply the functor, because the functor is inclusion, so it's just itself, this commutes. Yeah? But what does it mean? It means that G1 is equal to G2 H. And composition is multiplication in the group. So there is a unique morphism from G1 to G2 if and only if they represent the same group in the same element in G over H. If and only if G1H is equal to G2H. And otherwise, there are no morphisms. Okay? Otherwise, no morphisms. Okay, so what does that tell us about the homotopy type of the fiber? Well, it tells us that, that for a start, the group of components of this space, well, the group of components is given just by the morphisms that can be connected to one another by each of the components. So this is just G over H. So to see that this fiber is homotopy equivalent to this, we only need to check that each of the components is contractible. Right? And why? Well, each of the components looks like this. Each of the components looks like this. We have one object that we call G1. We have the identity. Then if they are in the same component, it's because they are related by an element of H, but only one. And here, the inverse, the identity, etc. And well, and we'll continue. But it's not hard to show that this category is equivalent to the category that has only one point and one morphism. So this is equivalent to this. Just pick one of them. And so each of the components is contractible. So we have proved that this is homotopy equivalent to G over H. Because to apply Cuidense theorem, we also need to check that these maps, we also need to check that we also need to check that given a morphism in the second category, the map induced in the other categories gives us a homotopy equivalence. So we need to check that this the one induced by G, we call it G star, gives a homotopy equivalence. But that's also quite easy to check. So I'll leave that up to you. Now, other maps that are going to be important, other homomorphisms, are conjugations. So what if then we have Cx, the maps given by taking an element of G and conjugating this element, where X is an element of G. Well, these morphisms are important in group theory, but it turns out that when you go to homotopy theory, they disappear. So one can show that BCX is homotopy equivalent to the identity on BG. And that's also not hard to show. You only show that the functor induced by Cx is naturally isomorphic to the functor induced by the identity to the identity functor. So how will that go? Well, if I have a morphism, say G, from a point to a point, and I apply the functor given by Cx, this is going to give me this thing. On the other hand, if I just take the identity, I have G over here. Well, a natural transformation is just a morphism, but has to be the same for each object. That makes this diagram commute for every G. So I believe that you have to pick X. Let me see. X, G composed with X is, no, X minus 1, I think. G, X minus 1 is the same as I do X minus 1, then I do that. So that shows that what we were playing. Is that clear? Yeah? Okay, what else do I want to say about this? Another thing that's not hard to show is that the fundamental group of BG is isomorphic to the group itself. And if you think about how the nerve of this category is, that should be clear. I mean, that's very easy to show. But moreover, and the universal cover, which is usually denoted by EG, is contractible. Okay. And this can also be shown categorically. I mean, most of the times you see this shown using principal G bundles. But you can also see that this cover can be constructed as the geometry realization of the following category. E.g., given where objects are elements of G and morphisms are given, well, I had to say where the morphisms from G to H is, Well, I'm going to make that this morphism set is only one element. So only one element that I'm going to call GH, just the pair GH. And the composition, well, there is a unique, so there's a unique way to compose them. Now, again, here we are in the same situation as before. We have a category where we have a unique morphism between any two objects. So again, this EG is contractible. Right? EG. I think I woke up with too much strength today. I'm breaking up my chalk. So this is contractible. And the covering map can also be realized at the level of categories. How? Well, we take all objects to the only object here, when we have no choice there, and each pair we send it to, I always forget this one, HG minus 1. Let me check just in case. This could be that, or could be the other way around. No, it's H minus 1G. So when you realize that functor, turns out to be a, well, up to homotopy is a covering space. And it's easy to check that the fiber is G. So, okay, now another important thing about the BGs that I mentioned but I haven't proved is that they are KG1s. So BG is a KG1 and this is going to be important for my last two talks, G is homotopy equivalent to loop space on BG. So the space BG can also be thought as a de-looping of the space G. In this case, it's discrete, but later it will be important. So how do we show this? Let me give you only the sketch. And we know that the universal cover is contractible. So there is a homotopy from the identity to where H0 is a constant and H1 is the identity. So let's compose this homotopy with the projection from EG to BG on the covering space. Compose the homotopy. So let's consider P. Well, given that I call that P, I should call the realization of P to BG. Okay? Now, if we look at the adjoint of this map, this is giving us, I think the adjoint is sometimes denoted something like this. So it's giving us a map from EG to paths on BG that start at Px0. Okay. Well, this I just mean alpha from I to BG such that alpha of 0 is P of x0. Okay? Now I'm going to use this map in the following way. I have my covering space, but then on the other hand, I also have a map from this space to BG, which is evaluation on the end of the interval. And as we know, this is the path space vibration. The fiber is just the loops on BG. The loops at, I should say P of x0. Okay? So in this way, we constructed a map like that. Yeah? And it's not hard to check that doing this is the same as doing that, and then the identity. So this is the map that I call that. So when we have a diagram like that, this is going to induce a map on the fibers. Yeah? So now what happens? Well, associated to any fibration, we have a long exact sequence of homotopy groups, right? One for this one and one for that one. And that long exact sequence is natural with respect to maps. So we're going to have two long exact sequences and maps between them. But on the other hand, these are contractible, both of them, right? So our long exact sequence is going to be kind of easy. So in a long exact sequence, the only interesting parts are going to be, well, pk of g to pk eg, pk g. And then we have the same thing down here. Oh. Well, I didn't write the ones that I should have. Let me let me continue one more. Okay, so these are the two sequences, and we have maps going this way. Now, forget about this. It was just didn't realize. So these are 0. Which means that these maps are isomorphisms. Okay? And also, this was induced by the identity. So this is also an isomorphism. Which means that these are also isomorphisms for all k. Okay? So we have a map, this map phi, that induces isomorphisms on all homotopy groups. So it's a weak homotopy equivalence. But also, G is a discrete group, so it's very trivially a CW complex. And this is also a CW complex, so it's a homotopy equivalence. So phi is a homotopy equivalence. Okay? And from the top row, from this isomorphism, we also see that BG is a KG1. Okay? So very nice spaces. Maybe this is enough of an introduction about classifying spaces. Okay, so what do I want to talk next? Now, if you have seen classifying spaces, it's probably because you were studying group cohomology. Right? So much of what I'm going to say next is motivated also by results in group cohomology. So let me leave that there and continue here. So let me pass to group cohomology. Now, group cohomology is just that, finding the cohomology of the group, which is defined as cohomology of the space, Vg, let's say with coefficients in Z. Now, this sometimes can be easy, but most of the time it's not. It is a hard problem to compute this. Okay, so yeah, there are many groups where you don't know, even for finite groups. Okay. So what one does is, well, let's change the coefficients to something simpler. So let me denote by Fp the field with P elements. So instead of computing that, how about I try to compute this? Fpg coefficients in Fp. And it turns out that this is I'd like to say easier, but it's really not that much easier in a way. Right? But it's easier in the sense that we reduce the problem and we reduce the quantity of groups that we have to deal with. So, well, let me stop talking and start writing. So this is really where we start to have this correspondence between the properties of groups and the properties of BG. So for each prime P, we know from group theory that we can find, yeah, just start by saying this. Let G be a finite group now. From now on. Now that's going to be important. So we know from group theory that every finite group and fix a prime, we can find a CILO subgroup. So there is a P CILO S of G. There's more than one, doesn't matter, just pick one. Well, let's consider what happens when we look at the inclusion of S into G. So for one hand, we have the map induced by the inclusion goes the other way, right? So let me call this the restriction from S to G. But on the other hand, I also prove that the inclusion of BS into BG is a covering space, right? So when we have a covering space, we have a transfer induced in the cohomology groups. So we have a transfer I'm also going to call transfer from S to G. Right? Yes?
So we're assuming that the G has some kind of P torsion with the same P as your FP.
Well, if it wasn't, then I would say that the P CILO is the trivial subgroup. And that will work too. But yeah, thanks. That's a tricky point, I guess. Yeah. Okay, but now what does the transfer do? Well, we take for each simplex and we lift it the number of times as the number of leaves that the covering space has. So if we do restriction and then transfer, what we are doing is just multiplication by the number of leaves, which we proved it was that. Or in other words, we also call this the index of S in G. Now, because CS is the P CILO, the index is prime to P. So the index is prime to P. And we are dealing here with, well, things that are sums of FPs, right? So multiplying by something that is prime to P is an isomorphism. So multiplication by this is an isomorphism. And if the sorry?
How is that an isomorphism?
How is that an isomorphism? Well, all these two groups, if you look at each stage, is just a sum of FPs, right? And in FP or in CP, if you like, multiplication by a number that is prime to P is an isomorphism, right? Okay, and now how does that help me? Well, if this is an isomorphism, this one has to be an injection. This implies that the restriction is injective. Okay, so In a way, this is nicer because we say, well, the cohomology of G, well, maybe I should put BG. The cohomology of BG is a subring of the cohomology of BS. Right? So if we could identify the image here, then we'll be done. Well, if we could compute this, that's another thing, of course, and then identify the image, then we will be done. So this is actually what Cartan and Eilenberg did. It's very interesting because it has to do with conjugations. So to identify the image, let's look at the subgroups of S. So say Q is a subgroup of S, and G is an element of the normalizer of Q in S. Now I'm going to explain what that is. This is just the elements of G such that H, Q, H minus 1 is contained in S. So the elements that normalize Q into S. So now we have two ways to put Q inside S. We can put it just by the inclusion, or we can put it through the conjugation, right? So let's see what happens if we take something in the image here and we conjugate it. What happens if we do the map induced by the conjugation to something in the image? CG star is the map induced by conjugation. So this will go to H star BQ. Now, one thing about this conjugation, we can see it the following way. We have Q, we have the conjugation, we also have the inclusion here of Q into G, and the inclusion of S into G, because this conjugation extends to the whole group. It's just the same CG, right? So now, doing restriction first and doing CG is the same thing as doing first CG, but this other CG, and then this restriction. So this is restriction of, I need to go back now. Restriction Q to G, CG star of Y. Okay, you agree with that? But now here is the interesting thing. This is a conjugation from the group to itself. And we prove that conjugation induces a map that is homotopy equivalent to the identity. So we kill that, and that's the same thing as this. It doesn't seem like we gain much, but let me put it in a different way. This is the same thing as restriction from Q to S, restriction from G to S of Y. Because restricting from G to Q is the same thing as restricting from G to S and then from S to Q. Yeah? So what have we really shown? If we think about these elements as a whole piece, we have proved that conjugating is the same thing as including in cohomology. So this is what I call the stable elements. So definition, an element C in the cohomology of PSFP is called stable if CG star of C is equal to restriction of QS of C for all subgroups and all G in the normalizer from Q to S. Okay? So what we have shown is that the image of the restriction falls inside the stable elements. And what the Cartan-Eilenberg says is that actually the image is just that, stable elements. So theorem, Cartan-Eilenberg. H BG FP is isomorphic to the stable elements of this cohomology. So this takes a bit more work. I'm not going to do it on the board. It wouldn't make sense anyway. It's not too hard to prove anyway. And you can find it, for example, in the book of Brown, group cohomology. But now this theorem tells me really something interesting, that if I want to compute the cohomology of BG, I only need to do two things. Compute the cohomology of BS and find the stable elements. How do I find the stable elements? I only need to understand two things. One, how the conjugations work, and two, how the inclusions work. Okay? So this is the motivation to introduce the following category. So let me introduce the, now I understand. So let me introduce the following category, FSG, which is called the fusion system of G with respect to S. And in this category, I'm going to put all the information that I will need to compute that, except for the cohomology of S. So it will be a category whose objects are the subgroups of S and whose morphisms so in these categories, I'm going to write my morphisms as home sets. are what we call home G from Q to R, which are G conjugations from Q into R. So they are maps. They are group homomorphisms from Q to R such that F is equal to C of G for some G. But it doesn't have to be an isomorphism, okay? It could be a conjugation in the sense that G, Q, G minus 1 is inside R. So it's a conjugation followed by an inclusion, yeah? Also keep in mind that we are not remembering the G, we are only remembering the map, yeah? So we can also write this in this form. Where, let me tell you what CGQ is, I guess probably you know, it's the centralizer.
US any group.
Sorry, what?
S is any group, subgroup of
Usually, I mean, you can put here any P subgroup, okay? And but usually we will use the Silo subgroup of G. I mean, the definition also makes sense for any P subgroup of G. But when you have that this subgroup is precisely the Silo, the category has better properties. So I was going to tell you what this is. The centralizer of Q is the elements of G such that GQ is equal to QG for all Q. Does it make sense that this is equal to that? Well, if it doesn't make sense, it's for the exercise section. But it's really easy to see. Okay, so now we understand this object that I stated at the beginning. This is the categorical part that really determines in some way the homotopy type of BG completed at P. Right? So at the beginning I said that BG was homotopy equivalent, sorry, BG completed at P was homotopy equivalent to BG prime completed at P if and only if we have an isomorphism of the Sylow subgroups, and this isomorphism induced an isomorphism of categories between the fusion systems. So now you can see that it's a really strong statement. Yeah?
So is the reason that the choice of S doesn't matter is that all the Sylow subgroups are conjugate, and so you can compose with those conjugations in that diagram you had before?
Can you repeat that again?
Okay, so
Yeah.
you're choosing an S, and if S is a Sylow P
Yeah.
subgroup,
Mm-hmm.
you said it computes with respect to that P.
Yeah.
Does the choice not matter because you
Yeah.
can use the conjugation between the Sylow subgroups to induce isomorphisms in cohomology?
Yeah, okay. So the question is, does the choice of S matter, right? And the choice of the choice of S doesn't matter because the Sylow theorems tells you that any two Sylow subgroups are conjugate to each other, right? So if you choose a different S prime and you have the F S prime, the two categories are going to be isomorphic. So, but yeah, that's a good question. I mean, in fact, what some people do, instead of starting from fixing a Sylow, you start by taking all the P subgroups of G. So it's a much bigger category. But what happens with that category is that the ones that are outside S, you can bring it inside. So it's still equivalent to this one. But it still makes sense. And when you consider all the P subgroups, that's something that was studied before by algebraists, and it was called the Frobenius category of G, which has an interesting algebra. Okay, so what else did I want to say? Okay, now I'm almost getting to the end of my time. But now with this category, I can also express this theorem in a different way. So now I can also write this in the following way. Consider the functor. Let me give it a name, capital F, from the fusion category to rings that on each object gives me the cohomology of BQ coefficients in FP. Okay? And on morphisms, well, it does the induced morphism on cohomology. Okay, now, considering that, I can rephrase the Cartan-Eilenberg theorem as follows. The cohomology of BG with coefficients in FP is isomorphic to the limit, to the inverse limit over the category FSG of the functor F. Okay? Or if you want to write it not so formally, the limit over the category FSG of that. Which, again, gives us the idea that, well, we only need to understand this category and the cohomology of S2. Okay, any questions about this? Okay, good. Now, so you realize that if we have two fusion systems that are isomorphic, then, well, if we have more, let me be more precise. If we have an isomorphism between two Sylow subgroups, and that isomorphism induces an isomorphism of these categories, then when I do the respective limits, I'm going to get the same thing, right? So the fusion system and the subgroup S determines this whole thing, that's for sure. But what I want to say, and what the conjecture says is stronger, is that it determines this. Now, this construction is very related to that, but it's not exactly the same. It's like rigidifying this. Right? So let me now, I don't know if I should start talking about P-completion with 2 or 3 or 4 minutes, but let me just start. So what I would like to talk next is about how to lift this to an isomorphism, to a homotopy equivalence of BG completed at P. So I want to talk about the P completion of classifying space. Okay. So we're fixing a prime, and let me tell you the idea of what the P completion is. Well, we're going to have somebody explain the construction. I don't know who, or I guess explain the construction. So what is P completion? P completion is a functor. So P completion is given by a functor from topological spaces to topological spaces that to a space assign another space denoted like that, together for a natural transformation from the identity to this. Together with a natural transformation from the identity to this functor. In other words, for each space X, I have a map from X to X completed at P. So I have a map. Now this construction, if you have seen it before, is quite brutal, right? I mean, it's really strange when you see the more general construction. But if you have seen, if you ever seen the P completion of Sullivan, which is sort of a particular case, only it works for simply connected spaces, it's not that hard to understand. It's just like finding the P parts. But when you are in such generality, there are some weird things that can happen. I mean, if you're working in abelian groups, and you take the P primary part of the abelian group, and then you take the P primary part of the P primary part, you would expect that you haven't done anything, right? But for spaces, that's not the case. There are spaces for which you P complete twice is not homotopy equivalent to P completing once. That's very strange. But of course, the construction is kind of weird too, so it's understandable. But we want to restrict our attention to spaces that satisfy this nice condition. So we say that a space is P good if XP is homotopy equivalent to the double P completion, which is something that we should expect, but it doesn't always happen. Fortunately, this is going to happen for the spaces that we're interested in. So we can breathe and be happy. And maybe I will end with this. So theorem. If X satisfies either A, X is simply connected, or B, all the homotopy groups of X are finite, then X is P good. Let me tell you why I like this theorem. I like this theorem because we are going to be dealing with X. It's going to be the classifying space of a group. If the group is finite, then we're going to be in this situation. Because either we have pi 1, which is G, it's a finite group, and all the rest are 0. Or if we have BG for a compactly group, although I haven't said anything about them, those are simply connected. So these are good spaces, really good spaces. Okay, I have a bit more to say about P-completion, but I will continue tomorrow.